So in the last section, we were looking at you place the solid compound in water, how much of it dissolves. Solubility told us, all right, how much of the solid in moles per liter will dissolve. And if you stay under solubility, you won't see a solid. But if you go over that solubility, then you will see a solid. That's one application of this kind of stuff, all right, like how much of something will dissolve. And if you have a compound which is not the best for the environment, you might be really concerned with keeping it under some kind of threshold value. And that's where those kind of things can be helpful. But what's probably even more applicable is this kind of scenario. This is now an example where we're using that weird mercury 2+ ion. And it also makes a very insoluble chloride. So the KSP for this reaction, if Hg2Cl2 is the reactant, then it would make the weird Hg2 2+ ion, which we'll see in lab actually, and 2 chlorides. So KSP, this is a solid, so we ignore that, but it would be the mercury ion times the chloride ion squared. And this value has been found to be 1.1 times 10 to the -18th. So again, very reactant favored, which means we'll see lots of solid, but because KSP is a number that's greater than 0, it means there will be a little bit of the mercury and the chloride running around. Now, why this problem is different is, let's say that I made a mistake and I added some mercury ion to some water, and we have a 0.010 molar solution of mercury that we don't want anymore. And mercury is not the best metal for the environment. Mercury has lots of problems you can read about and stuff. So let's say that we want to get rid of our mercury. Well, in an environmental context, getting rid of something usually means that you make it a solid, you filter it out of the water, and you take the solid and you send it someplace to be buried or burned. And in Oregon's case, out in eastern Oregon, Arlington area, they have these places where they bury compounds that nothing else can be done with it. And this would be an example of one they might bury. So, got this solution, we don't want it anymore. We want to get rid of it. And instead of just dumping it down the drain, we want to do the environmental thing, which is cool, and precipitate it out, and then send the precipitate to somewhere else. Not in my backyard. Anyway, prop that back on. So, if we know we can add chloride to the mercury ion, it should make the insoluble compound pretty easily. And knowing that, the question here, how much chloride will we need to just barely begin precipitating this Hg2Cl2 salt? All right, like we want to know the minimum amount of chloride we'll need to start seeing the solid. All right, and it's probably not going to be a very big number because the KSP is so small. But using this information, we can absolutely calculate it. We know what the initial mercury concentration is. We know what the KSP is. We want to find how much chloride is needed to start the precipitation process. And you can probably imagine that what we're going to do here, we're going to use this KSP value. We're going to put this number in for mercury, and we're going to solve for chloride. All right, and the number that pops out will be the minimum amount of chloride needed to begin precipitation. And it's probably going to be a pretty small number, again, because this KSP is so reactant favored. Let's confirm it. So, KSP 1.1 times 10 to the -18th. KSP is the product of maximum ion concentrations before you start getting into solids, all right? So that's really important. And if our mercury is 0.01, then we can figure out how much chloride is going to be needed to make the precipitate possible. And precipitation is only going to happen when the product of those ions is exceeded, i.e. when you go past the KSP. So what this means is that if our mercury is 0.010, we'll put that in there, and we're going to solve for chloride. And the number that pops out is literally the threshold between not having a solid and having a solid. All right, it's a real important number when it comes to chemists and stuff like that, figuring it out. So, without further ado, chloride is going to equal, chloride squared, will be KSP over the mercury. And earlier we saw the mercury was 0.010. So if you want to solve for just chloride, square root KSP over 0.010, that number comes out to be 1.0 times 10 to the minus 8 moles per liter. Is 1.0 times 10 to the minus 8 number, is that a big number or a small number?
Very small.
Very small, absolutely, all right? Most of our solutions in chemistry, 0.1 molar, roughly, give or take a couple orders of magnitude. This is many, many orders smaller than that. So this tells you, the chemist and everybody else that's interested, it's not going to take much chloride to make a solid happen. If you're at 0.9 times 10 to the minus 8th molar, which is really small, you won't see any Hg2Cl2 solid. But the minute you get above this, and it's not going to take much to get above this, then you're going to start seeing the solid Hg2Cl2. So in this problem, we had so much mercury, we've got the KSP. The chloride number we solve for is the minimum amount to begin precipitation, to begin seeing the solid. And we want to go in this problem beyond that number because we want to get the Hg2 plus out of solution. If we can get it into a solid, we can filter it out, ship it away, and hopefully do the environmentally right thing. Questions? Okay, so now that we know that chloride only has to be 1.0 times 10 to the minus 8th molar, the question is, all right, well, let's pump the chloride in. Chloride is cheap. Chloride is table salt, which we already talked about. It's an HCl. It's all over the place. And we really, really, really don't want to have mercury running around in solution. So let's raise the chloride now to 1 molar, all right? We're going to have 1 moles per liter chloride from sodium chloride, HCl, something like that. Now, before, the mercury was 0.010. As we start adding chloride, will that, by Le Chatelier's principle, make this reaction go more to the left, more to the right, or will it do nothing? To the left, that's right. If you add something, it moves to the opposite side. We're adding a ton of chloride here. And that's going to make this reaction move to the opposite side, to the reactant side. So we're going to see lots and lots of Hg2Cl2 precipitate. And in the process of moving to the left, the mercury, which was 0.010, is going to go down a lot. So we're curious, if the chloride is 1 moles per liter, what is the value of mercury at this point? All right, it won't probably be 0, but it'll be hopefully a number quite a bit less than 0.010. Any questions on what this question is asking? Cool. So mathematically, the new mercury is going to equal the KSP divided by our new concentration of the chloride. Technically, it's chloride squared. And again, this part just came from KSP equaling mercury times chloride squared, and we're solving for mercury. Well, 1.1 times 10 to the minus 8th divided by 1 squared is 1.1 times 10 to the minus 8th. And believe it or not, this is kind of cool for chemists, all right? So chemists can say that if you raise the chloride to 1 moles per liter, our mercury concentration went from a 10 to the minus 2, which is what this number is, down to a 10 to the minus 18th. So the difference between 10 to the minus 2 and 10 to the minus 18th is about 10 to the 16th. So what that means is we've drastically lowered the amount of mercury, all right? 10 to the minus 2 would be amount of mercury I wouldn't want to drink, all right? But 10 to the minus 18th moles per liter mercury, maybe I would drink that. That would sound safer by far than this one right here. So when chemists say they have taken something out of solution, I want you to realize what that means. Taking something out of solution means that you drastically lowered the concentration. All right, 10 to the minus 2 to 10 to the minus 18th is pretty great. But did the chemist totally take it out of solution? No. And this is something I want you to think of in the back of your mind. They'll say, oh yeah, the arsenic's been removed from your water. Not all of it, all right? There's gonna be a little around. And the question that you now need to think of as a human being and a scientist is, when is a substance safe? like probably 10 to the minus 18th mole of mercury, I would feel okay drinking, all right? Because that's really, really small. On the other hand, I mean, are you totally mercury free? No. All reactions are either stoichiometric or catalytic. Now, stoichiometric means a mole of this reacts with a mole of that. There's no stoichiometry going on with this kind of number. All right, so those kind of reactions, which are the big bad ones, flat out. But catalytic is something a little bit freakier, because in a catalyst, you just need a little bit of something to make something else happen. If there happened to be a catalytic conversion possible with this amount of mercury, that would be something to be worried about. So I want you to think about this on your own as like human beings, like when is something safe and when is something not safe? And I'm not here to tell you that. But what I can say is that someone comes to me and says, wow, I've got a situation contaminated with mercury. We can lower it quite a bit, absolutely. It won't be like 0, all right? But it'll be orders of magnitude smaller than it was. And in the chemistry world, that's kind of cool. Any questions on any of that? Okay, so here's a question you might see. Here's strontium carbonate, all right? We're trying to precipitate strontium carbonate from a strontium ion solution, all right? And the question is, what will be the concentration of the carbonate here? Well, KSP for strontium carbonate will be literally the product of the ions. So KSP would be the strontium concentration times the carbonate concentration. All of these KSPs you can see are just the product of the ions. So for strontium carbonate, that would be strontium 2 plus times the carbonate. Now in this problem, we have the KSP, we have the strontium ion, and we just want to solve for carbonate. So in this problem, what you would do is you would take the 5.6 number divided by the strontium ion concentration. The answer comes out to be 1.1 times 10 to the minus 8. So that's the amount of carbonate you would need to begin precipitating the strontium carbonate in this particular problem. Any questions? Okay, so this leads to a really kind of interesting idea, which is back to our friend the common ion effect. And we used common ion buffers to explain like why the weak acids and the weak bases can coexist, and what happens if you add a strong acid. It wipes out the weak base, but more of the weak acid is created in the process, blah, blah, blah. All right, here's an example of a solution. It's got some silver acetate, all right? And the silver acetate has some solid, and there's also some ions, all right? And silver acetate, like most of the silver salts, is kind of a boring white color. But anyway, all of a sudden, we're adding more silver ions to it, specifically silver nitrate. Silver ion is common to the silver acetate equilibrium. Like over here, you could write Ag acetate, making silver ions and acetate ions. Silver from silver nitrate is an ion that's common to the silver acetate solution. And by Le Chatelier's principle, adding silver should make the reaction go to the precipitate. So if you look like here, there's like 3 acetate ions running around. And after the silver nitrate's been added, there's only 1 acetate ion around. So we added silver, an ion common to the reaction that was there initially, and whatever the counter ion was, in this case acetate ion running around solution has gone down. But in the process, we end up adding more nitrate, and we'll talk about that here in a little bit. So in this example, pretend, which is not true, acetate is really dangerous, all right? We want it out of solution. All right, well, add silver nitrate. There's going to be less of that quote-unquote dangerous ion, but we do have to replace it with something. And that's something that you need to think about when you're doing these kind of reactions. So common ion is basically allowing you to push one ion back into solid, but you do end up adding something in its place, and that's something just to keep in the back of your mind. Okay.
In the test tube is a solution containing lead ions. To this we add a solution containing chloride ions, and lead chloride precipitates. Solid lead chloride is in equilibrium with lead ions and chloride ions in solution. At this point, we add more chloride ions in the form of a sodium chloride solution, which disturbs the equilibrium. More lead chloride precipitates, which removes still more lead ions from solution.
Okay, in this reaction, we've got some lead 2 plus floating around. And lead's not a good thing to have around stuff. They banned it in paint for a reason, right? Kids were always licking the paint and stuff like that. But anyway, we want to try and get lead out of solution. So if we make a solid with lead, we can then filter it, get rid of it, blah, blah, blah. So initially, we have lead 2 plus ions running around. Maybe it's lead 2 nitrate, some other kind of ion. And how we're getting rid of it is we're adding a chloride source, a sodium chloride, all right? Well, adding a chloride source precipitates PbCl2. PbCl2 is really insoluble. So there was no PbCl2, but then at this dashed line, we added some NaCl, and all of a sudden now we have PbCl2 as a solid, and that's good, we can filter it. In the process, the free lead concentration has decreased. We have less free lead in solution than we used to. However, by adding chloride, we do have now chloride in solution. We didn't have any chloride before, but now we do. So then at this dashed line, they added another sodium chloride amount. And this chloride, again, lowered the free Pb2+, so it's much lower than it was. We have more PbCl2 solid, so it's higher. But notice again, the chloride is even higher yet. So adding NaCl, we get rid of the PbCl2. We can filter that out, which is good. We're much, much, much lower on the free Pb2+. However, in the process, we of course have now chloride ions running around, and it doesn't mention it, but sodium ions are running around too. Sodium's usually pretty inert, but you never know. It's something to think about. So in these kind of problems, you want to get rid of some kind of problem ion, and in this case, that's definitely the lead 2 plus ion. So we definitely have gotten rid of that. This is the amount of PbCl2 we can filter out. But in the process, you replace it with something else. In this case, when there's more chloride, you'd have sodium ions running around, stuff like that. Any questions? Okay. So again, lead, mercury, these kind of metals and stuff sometimes can be really funky and stuff. Now, in this problem, barium sulfate is an insoluble barium compound. Most sulfates are aqueous, but there are a couple of them that are insoluble, and barium sulfate is one of them. So if you look up the KSP for barium sulfate, 1.1 times 10 to the minus 10. And we can write that as equal to the barium ion concentration times the sulfate ion. And remember that all these KSPs, it's always the solid in equilibrium with the ions. So the question is, we first want to find the solubility in pure water, and then we want to find the solubility when there's some barium ion present. Okay, so this first part is we want to solve for that X I was battling about earlier, all right? You want to find the solubility in pure water. And we saw earlier that solubility is equal to barium and the sulfate, because 1 mole BaSO4 makes 1 mole of barium and 1 sulfate. So we really want to solve for that solubility, that X number. And so X times X equals KSP, or X squared equals KSP. So if you want to solve for the solubility, you would take the square root of KSP. So in this case, the solubility, 1.0 times 10 to the minus 5. And again, what solubility means when you have this kind of problem is that BaSO4, once you go past this many moles per liter, you're going to see a solid. And it's not hard to get past 10 to the minus 5. That's a pretty small concentration. But in theory, if you were 0.9 times 10 to the minus 5, then you would not see a solid. But that's such a small number that that's going to be pretty easy to get to. So BaSO4 is going to be insoluble. You'll see it. This is a 1-to-1 ratio, KSP equals x squared, blah, blah, blah. Again, if you have a solid and you want to see how soluble it is in water, that's when you can use these x squared, 4x cubed kind of things, and you just figure out number of cations and anions. Any questions on that? Okay. Now, this is in pure water. Now, this is our equilibrium, barium sulfate equilibrium with barium and sulfate. In part 2, we're adding a source of barium, all right? So barium is a product. And as by Le Chatelier's principle, or common ion effect, you add a product, it's going to shift the reaction to the opposite side, it's going to shift it to the left. So the barium and sulfate ions are going to react to make barium sulfate. And we'll find the new solubility now in part B of this problem. So in pure water, barium sulfate dissolves 1 times 10 to the minus 5 moles per liter. But with barium sulfate, we've already got some barium, all right? And this is again good old Le Chatelier's principle problem. You start adding some barium, it should move it to the left side. You'll have more precipitate. But in the process, your solubility should decrease. Because remember, solubility is just how many of these crazy things are running around. If you start moving this to the reactant side, to the solid, that means your solubility should go down. So the common ion in this problem is barium. And every time you see common ion, you can just think about Le Chatelier's principle. And if you start adding barium ion, and you want to know which way it's going to shift the equilibrium, well, barium's a product, it's going to shift it to the left. It's going to shift it to the reactant side. So that means that less BaSO4 is going to be breaking down to the ions. So your solubility should be smaller in the presence of barium than it was in the presence of just water. So a lot of these problems, you can get a really good visualization cue if you just think about Le Chatelier's principle. Remember, you add something, it shifts to the opposite side. Shifting to the reactant side in these problems means less soluble. Okay. Any questions on that? Okay, so what you can do is set up like an ice table. And in this case, you've got so much barium to begin with now, 0.010, and you don't have any sulfate. Remember, at equilibrium, you have to have some of everything. So that means the sulfate will go up by Y, and barium will be the initial amount plus Y. I used Y here because I was using X for solubility earlier, and I want to point out that it's a different thing, even though it's, okay. So at equilibrium, your sulfate will be just Y, X, whatever you want to call it. Barium will be the initial amount plus Y, the amount that you're changing. And those things are just equal to KSP. So you can say KSP, the 1.1 times 10 to the minus 10, that equals 0.010 plus Y for barium and just Y for sulfate. Now at this point, this would be Y squared plus 0.010Y minus 1.1 times 10 to the minus 10th equals 0, a quadratic. But man, oh man, you've probably seen how chemists love to think about if this amount will change this number right here. And if you remember on the last problem, the value we had for solubility, which is what Y is in here, was like 10 to the minus 5. And 10 to the minus 5 plus this number, which is a 10 to the minus 2, it's pretty much going to stay 10 to the minus 2. And in addition, we predicted that adding barium will move the reaction to the left, so our 10 to the minus 5 number will probably be even smaller. So if you want to use the solve button at this point in the quadratic, you absolutely can, but I would just pull that little y out. It was already too small to make a difference relative to this number, and we're predicting it's going to go down even less. So if you pull the y out, that plus y, this problem becomes a heck of a lot easier. KSP equals just 0.010 times y. And if you solve for y, KSB divided by 0.01, 1.1 times 10 to the minus 8th. Now at this point, anytime you start using these approximations, you should think about if you're kind of in the right target or if you're totally out to lunch. And the question is, 0.010 plus this number, will it make a difference? And remember, by sig figs, you cut off at the largest doubtful digit. And this number has the thousandths, this 0, as the doubtful digit. Well, this number doesn't even start until several orders of magnitude to the right. So this plus this number is still going to be this number. So I would absolutely say you are quite all right in pulling out that plus y. You can still do the quadratic if you don't believe me, and that's okay. I'm not offended or anything, but trust me, man, just pull it out. It's too small, man. Finally, we predicted that by adding barium, the reaction would shift to the left, and that's totally what we see. It was 10 to the minus 8th in water, and now it's 10 to the minus 8th in the presence of the barium. So adding the barium shifted the reaction to the left. Your solubility went down quite a bit. It went down from a 10 to the minus 5 number to a 10 to the minus 8th. So summing all of this up, in pure water, solubility was 10 to the minus 5. In the barium, it was 10 to the minus 8th. So adding barium lowered the solubility. It made barium sulfate even less soluble. You're going to see more solid running around. And going through the ice table, even with the approximations, shows that Le Chatelier's principle is still cool. It's still being followed, even all this time. Questions? So let's say you had a cyanide compound, and you don't want cyanide running around in solution. You'd rather keep it as the solid. Well, if you can add whatever is complexing with the cyanide, it'll make your solubility go more reactant favoring. And what that means is you're going to have less cyanide in solution. You should have a safer thing environmentally to kind of keep it around. So you can affect solubility by adding these common ions. Any questions on them? This is another just fun video. This is barium sulfate being made. They use these super high resolution cameras to make some of these, and I'm always kind of fascinated. It's the artistic side after all of our math, I know, and stuff, so it's kind of cool to see. What the? Okay, let's talk about why I threw this video in there. I'll be honest, gang, solubility is, I think, the most boring topic of all chemistry 221 to 223, and I try and make it sound exciting, like, all right, adding barium makes it less soluble, but honestly, I find it a little boring, so I apologize. My jokes are most ineffectual in this chapter of all the chapters. This was this cheesy video that I got once. I used to be on this kind of art collective group, and they sent me this video. I was like, oh, that's so cool. I didn't know what else to do with it, so I thought, oh, this will spice up a boring solubility lecture. So anyway, just realize, I'm sorry, this is kind of a slow subject, I won't lie. It's super important, all right? You don't want to have junk running around in your waterways, right? And so controlling solubility gets it out, makes your stuff cleaner and better, and blah, blah, blah. But it's kind of dry. Anyway,
I was
Questions?
kind of curious if that was meant to be an advertisement for whatever's in the sperm.
Right on. This was a group from England, and it was like their proof of concept, like what they could do and stuff. And if you saw the movie Run Lola Run, I think that's the actress from that movie and stuff. But it wasn't like a specific for the vodka or whatever it is. You know, they were just trying to show things they could do. And I have no idea if they went on to make, you know, huge multi-million-dollar things, but it's kind of fun. Good. Other questions?
In the test tube is an aqueous solution containing ions of silver, lead, and copper. When we add chloride ions, a precipitation occurs, producing solid silver chloride and solid lead chloride. The copper ions remain in solution, indicated by the blue color of the liquid, which is decanted. We add distilled water to the test tube and heat it. Lead chloride is soluble in hot water and returns to solution. We again decant the solution in the test tube, leaving solid silver chloride. To demonstrate that the decanted solution contains lead ions, we can add chromate ions, which cause the precipitation of lead chromate. The characteristic yellow color of the precipitate confirms the presence of lead. We have separated the three ions in the original solution from each other.
So far in this section, we've seen how to figure out how much it takes to make a precipitate happen. So we use KSP and solubility, KSP equals x squared, etc., to find solubility. The second thing we did, we've got some mercury, we want to get out of solution, so we're using KSP to add like chloride, and we figured out how much mercury was left over at the end, blah, blah, blah. This is another thing that chemists do a lot, and it's basically separating out ions from each other. And in chemistry, one of the ways that chemists get paid a lot is separating out things, making them pure, more pure than they were. Because Mother Nature has things all together, jumbled together, and being able to separate them out is pretty cool. In this particular example, we have a test tube with copper, silver, and lead ions, all three. And we want to have just one of them, all right, ideally. So what people do is they looked up KSP values. Silver chloride is 1.8 times 10 to the minus 10. Lead 2 chloride, 1.7 times 10 to the minus 5. But copper 2 chloride, copper with chloride, is one of the AQ ones. If you remember from solubility, chloride, bromide, and iodide, insoluble when it's added with silver, lead, or the mercury ion. But basically everything else, it's AQ, and that includes copper. So I don't know of a KSP for CuCl2, which would be that. So what they did at the first step is they added a source of chloride, NaCl, HCl, whatever, some KCl, doesn't matter. And the Ag plus and the Pb2 plus made solids right away, but the copper didn't make any solids. So what they did is they decanted the liquid. And that means if you have test tubes, you can very gently pour the liquid off the other solid. So the solid stays in one liquid and the liquid goes in the other one. So that's how they got the copper out. Copper 2 plus has a cool blue color, so that's why that one is blue. But anyway, then they had a test tube with silver chloride and lead 2 chloride, which are both white solids. The next thing they did in this video was they heated it up. And in the Le Chatelier's principle, we actually heated the lead 2 chloride up and it went away, and then you cooled it down and it came back. Lead 2 chloride is as a definite temperature thing, which we'll talk about more in the next chapter. But anyway, heating up those solids in water, the PbCl2 actually went back in solution, while the silver chloride stayed a solid. So they decanted again, which got then the silver chloride solid in one container, and they had another beaker with silver ions. But did you really get the silver ion into solution? So what they did the last step, they added some chromate. Chromate with lead makes a really cool yellow color, and we'll see this yellow color in a future lab. If you add the chromate to silver, it makes kind of a red color. And the only thing I would have done differently on this lab is I would have added some chromate here just to make sure you see the red silver chromate color and you wouldn't see the yellow, but no big deal. But either way, by using these differences in solubility, you can separate copper, silver, and lead from each other. Now, it's not 100%. There's still going to be lead and silver over here, and in the lead one right here, there's still going to be some silver and probably some copper too. But most of it, all right, like I would say 90+%, maybe high 90+%, you would have most of them separated. And for most things, that's pretty good. So I want to show this video again, not the other one, sorry. I'll show this one again and kind of think about how they're separating them out based on their solubilities.
In the test tube is an aqueous solution containing ions of silver, lead, and copper. When we add chloride ions, a precipitation occurs, producing solid silver chloride and solid lead chloride. The copper ions remain in solution, indicated by the blue color of the liquid, which is decanted. We add distilled water to the test tube and heat it. Lead chloride is soluble in hot water and returns to solution. We again decant the solution in the test tube, leaving solid silver chloride. To demonstrate that the decanted solution contains lead ions, we can add chromate ions, which cause the precipitation of lead chromate. The characteristic yellow color of the precipitate confirms the presence of lead. We have separated the three ions in the original solution from each other.
So as a chemist, this is a big thing. You started with a mixture and you ended up with basically 3 separate groups, which is kind of cool. And again, knowing on these KSP things and how they work out, it's pretty handy. Again, copper doesn't make a solid. Only things with chlorides that make solids are silver, lead, and that mercury ion. So copper and chromium and sodium, etc., those would all make solutions, so you wouldn't see any solid in them. And then they use, by the way, color then to verify like what's happening in the different ones, which is kind of a cool thing too. Any questions on that? Now, here's the solution where we have silver ions and lead ions running around, and they're both 0.020 moles per liter. Chromate makes insoluble compounds with both. So look at these KSP numbers. This one's the KSP for silver chromate. This is the KSP for lead chromate. Both of these KSPs are less than 1. So that means that you're going to make a solid, a precipitate, both when Ag2CrO4 put together as well as when lead-2-chromate are put together. However, the numbers are not the same. There's a pretty big difference in their solubilities, and we're going to figure out what the solubilities are. So the first part of this question says, all right, we're going to slowly add in chromate to the silver and the lead. And the silver and lead, same concentration. The question is, which one precipitates first? Will we see the red silver chromate or the yellow lead-2-chromate? All right? And the answer for how we're going to do this is we're going to solve for chromate, all right, for both of these. We've got a KSP here for silver. We've got the silver ion. It's 0.020, square it. For this equation, here's the KSP for lead. Here's the lead concentration. We'll solve for chromate. If we have a 10 to the minus 5 and a 10 to the minus 8 moles per liter, the smaller moles per liter will precipitate first. It's going to take less of the smaller number to make a solid than it will the larger number. So that's kind of the punchline of how these problems work. All right? We're looking for the smaller chromate, and the smaller chromate will be the first one to precipitate. So we're going to pump the numbers in for silver and lead here a little bit, solve for the chromate, and we're going to look for the amount of chromate required to make a solid. And the smaller chromate is going to be the one that precipitates first. So, without further ado, the math is actually not too bad. We're just going to again calculate the chromate for both of these. So for the Ag2CrO4, here's our KSP. That equals silver ion squared times chromate. We want to solve for chromate, so we're going to divide by the silver ion squared. So the KSP for silver chromate divided by silver ion squared, 2.3 times 10 to the minus 8 molar chromate is required to make Ag2CrO4 precipitate. And that's not a very big number, all right? It's not going to be hard to go more than that number to make Ag2CrO4 precipitate. But now we're going to do the same kind of calculation, but for the lead. So lead 2-chromate has this 1.8 times 10 to the minus 14th number. And we want to dissolve by the lead to get the chromate. So KSP divided by 0.020, 9.0 times 10 to the minus 13th. So in this battle of small numbers, all right, 10 to the minus 13th is smaller than 10 to the minus 8. So that means that this number, which is the number required to make the lead chromate precipitate, this is going to precipitate first. It only takes 9 times 10 to the minus 13th moles per liter to make PbCrO4 begin to appear. It takes several orders of magnitude larger, 10 to the minus 13th versus 10 to the minus 8th. It takes several magnitudes larger to make the Ag2CrO4. So if we're really, really careful, if Alfonso and I are adding like 1.0 times 10 to the minus 13th moles at a time, which is really small but possible, we will see PbCrO4, the yellow compound, before we see the red Ag2CrO4. You have to be very controlled in how much chromate you add, but it is possible. And if this is important, we will see the PbCrO4 before we see the Ag2CrO4 compound. Yellow before red. Mathematically, take the KSP, divide by silver or lead ions. Silver here is squared, all right, because of the 2 right there. Finally, if you have to guess, if you don't want to go through all this rigmarole, usually smaller KSP will be the first one to precipitate. Usually. That's not 100%. Because of the squared part in there, you get yourself in trouble. But if you have to guess, and we've all been there, smaller KSP usually is the one to precipitate first. Okay. Any questions on that? Okay, so we've got silver and lead, we're adding chromate. Chromate with silver makes red, chromate with lead makes yellow. We just calculated this number is smaller than this one. We're going to see the yellow compound before we see the red compound. But really what this question we want to do is we want to set, whoa, sorry, I forgot about that part. Okay, right. It's been a couple years since I've done these lecture notes, so I apologize. That one caught me by surprise. Anyway, here's the question. We got 2 KSPs. We have some sulfite and some sulfate. Sulfite and sulfate. And the question is, which one precipitates first? Well, one way you could do this would be to take KSP and divide by the concentrations. But remember what I said earlier, if you have to guess, most of the time, smaller KSP will be the one to precipitate first. So in this case, because it's totally hit me by surprise, and I'm still waking up, caffeine hasn't totally kicked in yet, let's guess that calcium sulfite will precipitate first because it has a smaller KSP. And lo and behold, that's what we see, all right? Now, here's the actual math, all right, which I totally encourage you to do, of course, because this is that kind of class. You would take the KSP and divide by the appropriate concentrations. But again, most of the time, smaller KSP will precipitate out first, and that's definitely the case right here. The numbers 1.3 10 to the minus 7th is smaller than 8 times 10 to the minus 5. So again, that means that this one will begin to make a solid before this one will right here. Any questions on that? Okay. Now, in this example, we saw earlier that the lead 2 chromate begins to make a solid before the silver chromate happens, all right? This is another part of these kind of questions which often pops in. This question says, how much of the lead ion is still around when the silver ion just begins to precipitate? Now, if we're trying to separate lead from silver, and you start very slowly adding silver, in the last part we saw that, the lead-2 chromate is going to precipitate first. But as that precipitates, this number is going to start decreasing. So this question says that when you get to the point where the silver chromate begins to precipitate, how much lead is left? And this is another kind of cool thing, because as the PbCrO4 precipitates, the lead ion begins to drop out of solution. So in this kind of question, all right, we're going to use the chromate number from the last slide. The chromate required to make the silver chromate precipitate out, and I think it was a 10 to the minus 8th number, all right? We're going to use that chromate, but in the KSP for PbCrO4, because to get to the point where the silver precipitates, we need to know how much chromate is there. We're going to solve for lead, and hopefully the lead number we solve for will be smaller than the lead that we started with. So in the last slide, we calculated that the chromate we needed to make the Ag2CrO4 was 2.3 times 10 to the minus 8. And that was a bigger number than the 10 to the minus 13 or whatever the other number was. And we saw that, the lead will begin to precipitate. So in this question it says, when the chromate gets to 2.3 times 10 to the minus 8, how much lead is left? Like it was 0.020, how much is left when the chromate is at this point? And remember, as chromate goes up, your lead ion concentration is going to go down because you're going to make PbCrO4. That's no longer solution lead, that's complex lead. So how much of this stuff is left? Really good question. Mathematically, it's not hard. We're going to use the KSP for PbCrO4, but we're going to put the chromate from the silver chromate in here. We're going to put this number in right here, and we're going to solve for the lead. So mathematically, the KSP for PbCrO4 divided by the chromate when the silver begins to precipitate, which is 2.3 times 10 to the minus 8. This divided by that, lead is 7.8 times 10 to the minus 7th. And chemists collectively jump for joy here a little bit because the lead was a 10 to the minus 2. This number would be 2.0 times 10 to the minus 2. And now it's 7.8 times 10 to the minus 7. So that's dropping your lead concentration quite a bit. And if you're trying to get rid of the free lead, this would be a good thing. Also, if you bring the chromate to this level and you take out the solid PbCrO4, your lead concentration now is quite a bit less than it was. Your silver would still be 0.020 at that point. So this is how chemists think about separating out ions from each other. So this is a real common kind of problem when it comes to solubility problems in chemistry. So just FYI, first question, which one precipitates first? All right. The quick way, usually smaller KSP precipitates out first. But to do the second part, we do need to calculate how much chromate was needed to make the other more soluble one precipitate. So notice that in this part, 2.3 times 10 to the minus 8 came from this calculation. We put 0.020 squared in. We solved for chromate to get this number. And this number we put back into the less soluble one, which was lead-2 chromate. We solved for the new lead. The new lead should be a number less than what you started with. Sure enough, quite a few orders of magnitude smaller. And chemists are happy with these kind of numbers because it shows them that the ions have been separated. Any questions? Okay, let's take a 5-minute break or so. It's about 10:53, 10:58 or so. We'll come back and hit this stuff.